Hey, I'm recording this video about the blog post I wrote that is like neural networks. So I'm gonna cover just some points. I'm not sure which is the hardest point, but I think the blog post was too dense and it wasn't my idea and my goal. The initial thought about the blog post was like I'm trying to simplify these complex things, and I hope anyone can understand with enough willpower and time. So let's go. Just passing in the high level, the perceptron, which would be like one neuron, and there is, but the only output is yes or no. I'm not gonna talk more about that because I think it's simple enough in the blog post. But I'm gonna talk about the training and the learning age. I think the learning age mainly is really important, and I don't know if I talked about enough. So start with the learning age. I think the important is graph and plot to be simplified because when I say small learning rate, it's not like a fixed value. You actually can try multiple values, and if you have enough hardware to actually process, you can just do a lot of small learning rate numbers. So we're gonna jumping a little to the best output. That, that is like the minimum error setup. And while the learning rates, you can just go like farther from the actual bed setup. And I think this is the most important thing in models in general, not just the perceptron that I removed the perceptron that I wrote about. It's like the main and the core of neural networks. So this learning rate is actually I think you actually use to don't fall to the way of like overfitting that I also wrote about. And I think I wrote enough about that, but it's actually a really important point because if you are trying to train a model and you overfit, you actually don't, you can't use the model because overfitting is like the model is specialist in your data set, but it's not specialist in the behavior. So you can't use this model in anything besides this data set, which is like not usable. You want to use your model more in actual data than the data set and the training. So the learning rate is one of the most important things about the mean square error and the squared error that I wrote about. I think it's important to say that there is more than there's other functions of errors, and I think you shouldn't focus on that. When you actually have the deep understanding, you actually can choose which one you're gonna use. So actually, in the blog post, I just talked about some like square error and these error functions, and I don't think I'm gonna go deeper because I think the blog post is enough for that. But I think the error surface and minima is some important points that don't maybe I don't talk about enough. And this plot is like this is one wave, this is other wave, and this is the sum of square error. This could be the mean square error too, but this situation is just a sum because it's simplified and it's easier to say. When you have this convex surface, like to the border, is like higher. It's just that it's more sum of square errors. So you want the opposite of that. That's like this line that's pointing to the optimal setup. And this is gonna happen for basically any surface you can. I think any Euclidean surface, you are gonna find the minimum if you use the derivative of the mathematics of the error function. This is a thing I'm gonna talk about more, but just for clarification for this plot, this line is pointing to below is like the optimal setup. Of course, if you're trying to find the minima here, you are gonna find a minima, but a local minima instead of the global minima that I talked in the blog post. The global minima is like the whole surface the function actually generates. It's the optimal. And it's a bit hard to actually go for the global minimum in terms times that you can or you don't want because it's like too expensive. But usually, as far as I know, it's like a one big step. There is like some tests that after this big step, what happened? So if the sum of square error is below the other one, because you already reached some local minimum, and after this big jump, you like go for another even minimum. You find another minimum that is even minimum than the local minimum. So this is important point. I think there is the gradient descent algorithm that I don't know if it's enough simplified, but you can think of that like there is no error function that you aggregate all the errors you get from the inputs after calculating the weights and these things. You just want to find the derivative of this generated function. Why? Because the derivative of some function will be the slope of the function. So you have like a direction of the function is pointing towards. Of course, the function is pointing to the steepest ascent. So you don't want that because if you look for this graph or even this graph, if you go for the steepest ascent is like the one with the most errors. And the errors not necessarily goes from one to zero from one. Of course, then if it's wrong, it's wrong, and if it's right, it's right. But the error size can be bigger. For example, you can like miss so much that the actual value that goes for here is 1.6 to 0.22, but you could like in this situation isn't possible because the surface is like simple, but we can think that some wall would be for here and here would be like 25 of error and you like point to this one, but you don't want this deepest accent. This is the whole point. So you just use the negative of the gradient of the derivative. That would be the local minimum or the global minimum depending on the situation. So it's just a way to find the optimal setup for your error function. There is not any magic associated. It's just one function and you find the slope pointing towards the most efficient situation that can be or not the global best situation. Sometimes less the local minimum. As I said before, the learning rate continues to work the same as I said before. There's like you go small steps or big steps towards the minimum, but you can just do a massive step outside the minimum and arrive at somewhere that is like even worse. There's the problem with the square, sine square error that I said before. When you go to sigmoid functions, it doesn't work too well. But when you don't go to this square error and go for other functions that I said after the binary cross interrupt, for example, that focus the even if it's too small or too big, it like have the same keyword for the function or the learning age. I'm not gonna enter this point because I think I could say talk only about binary cross entropy afterwards or in other videos, but I think it's important to say the sigmoid functions and this one in specific I think it's like a bit too ugly as a function, so people just see and don't want to understand what this means. Also, the derivative of the sigmoid flattens even more than the 0 to 1. The top of the derivative, the maximum slope is 0.25. So you kind of lose the you kind of lose what you you would gain from some square function we saw before, the same square or the mini square, because if it's too much to the error side or too much to the right side, it's gonna be flattening like that, like the zero from the start and the zero to the end. So I think this is the most important part. I don't think the binary cross entropy can be too much simplified, but I mean, I think reading enough times it makes sense. And in the end of the day, you just have to imagine a changes plot that goes how much he was the function or how much it fixed the function based on this plot. It's like it's not that hard, I guess. And about the backpropagation algorithm, it's just a derivative I told before, but you have multiple steps. But as I said in the blog post, like the chain rule from calculus actually does give this powerful rule that you can have multiple functions and like do the derivative of all of this and find the actually slope of the function that would be the union of all functions. So one way or another, you would find the most efficient iteration, even if the function is like complex. For example, there is multiple neurons on multiple layers. It just changed the way you sum numbers and you multiply numbers. So it's just a derivative. And in the end of the day, it's like just the steepest ascent that we saw before. And like these have two weights, but per multi-layer, per multi-layer, it would be more size that like higher level dimensions. In this case, we can see because three dimensions, it's two weight, one weight one, weight two, and the actual sum of square errors. But you could have like 1,000 weights and even more, a million weights or even billion weights if you think about some transformers in his large language machine, large machine learning LLMs. So it really doesn't matter how complex the function is. You just do the derivative of this function and you find the optimal setup. And you don't even have to visualize this function or understand what this actually means in mathematical terms. It's just a derivative. So and usually the derivative becomes really simple. And of course, there is some properties we can use that like we calculate only one time the last function that we are going to apply for other functions, which actually simplifies a lot in computational computation. I'm gonna write about the computation parts and vectors usage later because I think it doesn't make sense. It's gonna be too much for this video and this blog post, but I think for the start and for the first video and the first moment, this is enough. I maybe when I try to explain these math parts, I'm gonna go to the notebook. I'm not sure. So that's all.